Where does sea sand actually come from? You're walking on a beach. The sun's warm on your skin, and you feel that perfect, grainy texture of sand between your toes. It's one of life's simple pleasures. We build castles with it, relax on it, and find it in our bags for weeks after a vacation. It's just sand. It's just there. We're so used to it that we've almost stopped questioning it.
But have you ever really stopped to think about what you're walking on?
Have you ever picked up a single grain and wondered about its story?
Most of us think sand is just tiny, ground-up rocks.
And while that's not totally wrong, it's like saying Moby Dick is just a book about a whale. The truth is a wild, almost unbelievable journey that spans millions of years. Connects towering mountains to the deep ocean and involves everything from the colossal power of glaciers to the digestive system of a brightly colored fish. The great environmentalist Rachel Carson once wrote, "In every curving beach, in every grain of sand." And that story is far more epic than you could ever imagine.
What if I told you that the pristine white sand of some of the world's most beautiful beaches actually came from the poop of a parrotfish?
It's true. And that's just one chapter in the secret life of sand. That seemingly boring little grain of sand under your foot is a survivor. It's the final product of a relentless, violent, and incredibly long process. It's a time traveler, a storyteller, and a tiny, tangible piece of our planet's deep and dynamic history.
In this video, we're not just going to look at sand. We're going to follow it.
We'll trace the epic geological and biological story of how a single grain of sand is born. How it travels, sometimes for thousands of miles, and how it finds its final resting place on your favorite beach. By the end, you'll never look at a beach the same way again. This isn't just a story about rocks. It's the story of our world, told one tiny grain at a time. Our story doesn't start at the coast. It starts hundreds, or even thousands of miles inland, deep within the heart of a colossal mountain range.
Picture a massive mountain of granite, a seemingly eternal and indestructible feature of the landscape.
This granite is what geologists call an igneous rock.
Born from molten magma that cooled and solidified deep within the Earth's crust millions of years ago. Inside this granite, our future grain of sand exists, but not as sand. It's locked away, a prisoner in a crystalline matrix. It's a tiny crystal of quartz, one of the most common and durable minerals on Earth. Alongside it are other minerals, like feldspar and mica, Quartz is incredibly tough, made of a strong lattice of silicon and oxygen atoms.
Feldspar, on the other hand, is a bit softer, a bit more susceptible to the ravages of time. This difference in durability is a crucial detail in our story.
For eons, our quartz crystal sits in darkness, under immense pressure, part of a silent, unmoving mountain. Continents drift, dinosaurs come and go, ice ages advance and retreat, but our grain remains locked in stone.
The mountain itself is a product of immense geological forces.
The slow, powerful collision of tectonic plates that crumpled the Earth's crust and thrust these rocks skyward.
But the very forces that build are also destined to destroy.
The moment a mountain is born, it's also sentenced to death.
A slow, grinding death by 1,000 cuts, a process we call weathering.
And this is where our grain of sand's journey toward freedom truly begins. Weathering isn't a single, dramatic event. It's a slow, relentless assault by the elements, a war of attrition fought over millennia. It happens in two main ways: physical weathering and chemical weathering. Think of physical weathering as the brute force attack. Every day, the sun heats the surface of the granite, causing it to expand just a tiny bit. Every night, the rock cools and contracts. This endless cycle creates stress.
Now, imagine a tiny crack in the rock.
Rainwater seeps into this crack. If the temperature drops below freezing, this water turns to ice.
As water freezes, it expands by about 9%, acting like a tiny, powerful wedge.
This process, called frost wedging, pries the crack open a little wider.
Year after year, century after century, the cycle repeats.
Freeze, thaw, expand, contract.
The tiny crack becomes a fissure, and the fissure becomes a fracture. At the same time, the mountain is assaulted by wind, which carries smaller abrasive particles that sandblast the surface. Plant roots, in their slow, persistent search for nutrients, can work their way into these cracks. And as they grow, they exert a surprising amount of force, widening the gaps further. All of these physical forces work together to break big rocks into smaller rocks. But there's a more subtle, and maybe more powerful, force at play: chemical weathering.
Rainwater isn't just pure H2O.
This acid is the great dissolver.
When it seeps into the rock, it begins to alter the mineral composition.
It has little effect on our tough, resilient quartz crystal.
But the feldspar and mica that surround it are a different story.
The acid attacks the feldspar, breaking it down into soft clay minerals. This is the critical step.
As the feldspar crumbles into clay, the strong, interlocking structure of the granite is compromised.
The cement holding the quartz grains in place begins to fail. Our grain of sand, once an integral part of a mighty mountain, is now precariously perched, held in place by weakened, decaying minerals, waiting for the final push that will set it free. After millions of years of imprisonment, its escape is imminent. The moment of release is often violent and dramatic.
It could be a torrential downpour that saturates the weakened rock and soil,
turning the mountainside into a slurry.
Gravity takes over, and a landslide rips a massive chunk of the mountain away, sending a chaotic mixture of boulders, pebbles, and newly liberated grains of sand tumbling down the slope. Or maybe it's a flash flood, a wall of water surging through a gully, with enough power to pluck our grain from its rocky home and sweep it into the current.
This is erosion, the process of carrying the weathered material away. Our grain of sand is finally free from the rock that held it for ages.
But it's not yet the sand we know.
It's likely still angular, sharp-edged, and mixed with a motley crew of other rock fragments.
It's now officially sediment, loose material, and it has just begun the longest and most transformative journey of its life. Our grain gets swept into a small mountain stream, a turbulent, high-energy environment. With every collision, the sharp edges of our quartz grain are chipped away.
It is slowly but surely being rounded and smoothed.
The less durable minerals that came along for the ride, like the remnants of feldspar or mica, are quickly broken down into even finer particles, silt and clay, which are carried along suspended in the water, often giving the river a murky, brown look. Our quartz grain, being tougher, survives this brutal process, but it's forever changed by it.
As the small stream flows into a larger river, the energy changes.
The slope is less steep. The water moves more slowly. Our grain of sand can no longer be carried in the main current.
Instead, it begins to bounce and roll along the riverbed, a process called saltation.
The grain becomes smaller, rounder, and more polished.
It's also being sorted.
The river's energy acts as a filter. Heavier gravel and pebbles are left behind in the upper reaches, while the lighter silt and clay are carried far out to sea. Sand, being in the middle, is transported steadily towards the coast.
Finally, after a journey that may have taken thousands of years, our grain of sand approaches its destination, the ocean.
As the river meets the sea, its current slows dramatically.
The last of its energy dissipates, and it can no longer carry its load of sediment. Our grain, along with billions of its companions, is dropped from the water and settles on the bottom.
It has arrived at the coast, but its story isn't over. The final, crucial chapter of its transformation is just about to begin.
The beach isn't yet made. It is forged in the chaos of the coast. Arrival at the coast is like entering a new, even more violent stage of the rock tumbler.
The forces of the ocean are relentless.
The constant action of waves, tides, and currents takes over the job of shaping and sorting the sand.
Imagine the motion of a wave.
As it approaches the shore and the water gets shallower, the wave breaks, releasing a tremendous amount of energy. And
the water that rushes up the beach is called the swash.
It picks up our grain of sand and carries it up the slope.
Then, gravity pulls the water back down the beach as backwash, dragging our grain with it.
This endless cycle happens every few seconds, 24 hours a day.
It is the ultimate polisher. Any remaining rough edges on our grain are smoothed away. And it becomes beautifully rounded. This wave action is also the final sorting mechanism. The churning water keeps the finest particles, the silt and clay, suspended and carries them further offshore into calmer water. What remains in the zone of breaking waves is the material we call sand.
Particles of a specific size, typically between about 0.06 and 2 millimeters in diameter.
So, a beach is essentially a giant concentration of sorted grains, deposited there by the tireless work of the waves. But sand on a beach is rarely stationary. Have you ever noticed that a beach can look different from one season to the next? That's because the sand is constantly on the move. One of the most important processes driving this movement is called longshore drift. Waves rarely approach the shore perfectly straight on. They usually hit the coastline at an angle, driven by the wind.
This means the swash, the water rushing up the beach, also moves up at an angle.
However, the backwash, pulled by gravity, flows straight back down the slope.
The result is that our grain of sand travels in a zigzag pattern along the coast.
Pushed up at an angle, dragged straight back down. With every wave, it moves a tiny bit further down the beach. Multiply this tiny movement by millions of waves per day, and you get what is essentially a river of sand flowing parallel to the coast.
This river can transport enormous quantities of sediment, constantly reshaping the shoreline.
It erodes sand from one area and deposits it in another. A single grain of sand might not stay on one beach for long. It could be part of a slow-moving procession, migrating along the coast for decades.
The energy of the waves also dictates the shape of the beach.
During the summer, calmer waves tend to build the beach up, creating a gentle slope.
In the winter, powerful storm waves do the opposite.
They scour the beach, dragging sand away and storing it in offshore bars.
This is why beaches are often steeper and narrower in the winter.
The sand isn't gone, it's just being temporarily stored underwater,
Waiting for summer to bring it back.
So, a beach is not a static place. It's a dynamic, living environment, a battlefield between the land and the sea, with sand as the ammunition. Our grain of sand, born in a mountain and carried by a river,
Is now caught in this coastal dance, constantly being shifted, sorted, and reshaped by the immense and ceaseless energy of the ocean.
So far, our grain of sand has been a piece of quartz.
This is the story for the majority of the world's tan-colored beaches. But what about the brilliant white sands of the Caribbean? Or the pink beaches of Bermuda?
For that, we need a completely different origin story.
It's one where biology takes the lead, though geology still plays a crucial role.
Let's travel to a vibrant, tropical coral reef.
Here, the source of sand isn't mountains of granite, but the teeming life of the ocean itself. This is called biogenic sand, meaning it comes from living organisms.
The primary contributors are corals, shells, and the skeletons of countless marine creatures.
Coral reefs are vast, underwater cities built by tiny animals called coral polyps,
which create hard skeletons of calcium-carbonate.
When these organisms die, their skeletons and shells are left behind. The same powerful waves and currents that grind down mountains smash and grind these skeletal remains into sand-sized particles. But there's another, even more fascinating process at work here: bioerosion.
And the star of this show is the parrotfish.
Parrotfish are brightly colored residents of the reef, named for their powerful, beak-like mouths.
They don't eat live coral, but rather the algae that grows on its surface.
They aren't delicate eaters. To get the algae, they use their strong beaks to bite off and swallow chunks of the coral skeleton. Inside the parrotfish, they have a second set of teeth in their throats, a pharyngeal mill, that grinds the hard coral into a fine powder. The fish digests the algae, and what comes out the other end is pure, fine-grained white sand.
A single large parrotfish can produce hundreds of pounds of sand this way, every single year.
On some reef-fringed beaches in places like Hawaii and the Caribbean, scientists estimate that a huge fraction, sometimes up to 70% of that beautiful white sand has passed through the digestive system of a parrotfish.
So when you're wiggling your toes in that powdery white sand, you are, in a very real sense, wiggling your toes in parrotfish poop.
But parrotfish aren't the only biological sand makers.
There are also tiny, single-celled organisms called foraminifera.
These microscopic creatures build protective shells. When they die, their immense numbers leave behind vast deposits of these tiny shells. On the beaches of Bermuda, a specific species of foraminifera has a reddish-pink shell. When these shells mix with the white sand from corals and other organisms,
They give the beaches their famous and beautiful pink hue.
so a grain of sand on a tropical beach has a life story that is worlds away from our quartz grain. It didn't begin in a mountain. It began as part of a living creature.
It is a direct link to the vibrant, living ecosystem just offshore.
Now that we know sand has two very different origin stories, one of rock and one of life, it starts to make sense why beaches around the world look so different.
The color of sand is like a fingerprint. It tells you exactly where it came from and what its journey was like. Let's start with the most common color, the light brown or tan sand we see on most continental beaches.
This color comes from its mineral makeup.
As we saw, the most durable mineral that survives the long journey from the mountains is quartz. Pure quartz is clear or white, but it's often tinted by iron oxide, which gives it a light brown hue. This sand is also mixed with feldspar, another common mineral that is naturally brown to tan. What about the dramatic black sand beaches you see in places like Hawaii, Iceland, and the Canary Islands? These beaches are a telltale sign of a volcanic past.
Their sand comes from the erosion of dark-colored volcanic rocks, like basalt. When molten lava flows into the cold ocean, it cools and shatters so rapidly that it can explode into glassy black fragments, forming a new beach almost overnight.
Some volcanic beaches even have green sand. The famous Papakulea Beach in Hawaii gets its unique olive green color from a mineral called olivine.
A nearby volcanic cinder cone is rich in this mineral.
And as the cone erodes, the heavy olivine crystals are concentrated on the beach by the waves, while lighter fragments are washed away. Then there are the red sand beaches, like those on Prince Edward Island in Canada. This striking color comes from rocks with a very high concentration of iron. When these rocks weather, the iron oxidizes. It essentially rusts, staining the sand grains a deep, rich red.
And of course, we have the white and pink sands of the tropics. As we learned, these are biogenic.
The brilliant white comes from the ground-up calcium-carbonate skeletons of corals and other organisms. And the pink sands of places like Bermuda are a mixture of that white sand with the red-shelled remains of foraminifera.
Every grain of sand on a beach is a clue.
The color, the size, and the shape all tell a story.
Coarse, angular grains suggest the sand is a young and hasn't traveled far. A beach with a mix of many different colored grains tells a story of a complex local geology.
A beach with very uniform grains tells a story of long-distance transport and incredible sorting by rivers and waves.
By simply looking at the sand, a geologist can start to read the history of the landscape, stretching back millions of years.
The next time you stand on a beach, take a moment.
Reach down and let a handful of sand run through your fingers. Don't just see sand. See the mountain peaks where it was born. See the eons of freezing and thawing that cracked its rocky prison. Hear the roar of the ancient river that carried it for 1,000 miles, tumbling and shaping it. Feel the thunderous crash of the waves that sorted, polished, and finally delivered it to the shore. If you're on a white sand beach, imagine the vibrant coral reef just beyond the waves. Picture the parrotfish, methodically crunching away, creating this paradise one mouthful at a time. Recognize that every single grain has a story. That tan-colored quartz grain might be a billion-year-old piece of the Earth's continental crust. That speck of black basalt might have been molten lava just a few centuries ago. That tiny pink fleck might be the shell of a creature that lived and died last year. A beach isn't just a pile of tiny rocks.
It is a destination. It is the endpoint of countless epic journeys.
It's one of the most dynamic environments on the planet, a place of constant creation, destruction, and movement.
It is a library of geological and biological history,
where every grain is a book, and every book tells a story of time, pressure, and transformation. The sand beneath your feet is a testament to the immense, slow, and powerful forces that shape our world.
It is the story of the Earth, and you are standing right in the middle of it.
If you were fascinated by the secret life of sand and want to uncover more stories hidden in our everyday world, be sure to subscribe.
We have a lot more epic journeys to explore.
And let us know in the comments, what's the most interesting beach you've ever been to? And what color was the sand?
Thanks for watching.